The next application of integrals that we're going to talk about is we're actually going to talk about a special category of integrals called improper integrals. So here I have just kind of my basic definite integrals, right? What it looks like where I've got bounds from a to b, and I'm taking this integral of a function, and I get out some value L, right? Remember, with definite integrals, your output is some number. It's not a function, it's a number. Well, what an improper integral is if infinity becomes involved as we work through these integrals. So that could look like one of the following. Either a is equal to negative infinity, right? Your lower bound, either you're starting at negative infinity or you're ending at positive infinity, so your upper bound is infinity, or the result you get is some sort of infinity, either positive infinity or negative infinity. Okay, so just to help you understand, just to give you an example, consider this problem. I'm doing the integral from 0 to 1 of 1 over x dx. Now, of course, neither of my bounds are infinity here, so it's not immediately obvious this is an improper integral. But if I try to evaluate that, check out what happens. Okay, what's my antiderivative of 1 over x? My antiderivative is the natural log of x, the absolute value of x. And I need to evaluate that from 0 to 1. What do I get when I plug in 1? Okay, I get the natural log of 1 minus the natural log of 0. Natural log of 1 is just 0. But what's the natural log of 0? That's actually going to give me an undefined value. So instead, I can think about this in terms of a limit. What is the limit as x approaches 0 from the positive direction of the natural log of x? We know I'm approaching from the positive direction because look at my interval. My interval is from 0 to 1, so I'm working with positive values. This limit is actually infinity, right? If you look at the graph of the natural log of x, the graph of the natural log of x goes something like this. Ooh, I said it wrong. It's not positive infinity, it's actually negative infinity. The reason why is because there's your graph of natural log. As you get close to 0, your function is just going down to negative infinity, right? So that means the natural log of 0 is negative infinity, and I end up with my definite integral equaling an infinite value. So that's why this ends up being an improper integral. Why is that? Well, if you actually graph 1 over x, the graph of 1 over x looks like this. There's an asymptote at 0. It has a vertical asymptote, which means this graph is going straight up to infinity. And if I try and integrate this area under the curve from 0 to 1, I'm going to get an infinite area because that just goes up to infinity. And that's what makes this improper. Now we might be thinking, oh, well, doesn't that mean that all of these integrals are going to go to infinity? Well, let's take a look at an example where that's not necessarily the case. Okay, take a look at this example. Now this is obviously an improper integral because one of my bounds is infinite. My upper bound is positive infinity, and we said, right, that causes my integral to be improper. So we might automatically think, oh, well, that means I'm letting x get infinitely large, so of course my area is going to be infinite. If my area doesn't have a stopping point, doesn't that mean it's going to be infinite? Well, take a look at what happens when we do this mathematically. Okay, I'm going to go ahead and take the antiderivative here, which means it might be nice to rewrite this as a power function, so I get 1/9 x to the negative second dx. When I take that antiderivative, I get 1/9 x to the negative first over negative 1. Okay, evaluated from 2 to infinity. Let me simplify that just a little bit, and I get negative 1 over 9x evaluated from 2 to infinity. Okay, so now I can go and evaluate it at my two bounds. Well, what happens when I evaluate this at my upper bound? What happens when I plug infinity into this function? Because x is in the denominator, I get negative 1 over infinity, right? 9 times an infinite value is still infinite. If your denominator is getting infinitely large and your numerator is staying constant, what's happening to your value? What's happening to your fraction? It's getting infinitely close to 0. So it turns out that this term just goes to 0. And then my second term is finite because I'm plugging in a 2. Sorry, this should be a negative because I subtract and then my integral is negative. So 1 over 9 times 2. And I'm left with the two negatives, the minus and the negative cancel out, and I'm left with 0 plus 1 over 18, which is 1 over 18. So somehow my integral, even though it goes to infinity, the area under the curve ends up being finite. And this is a cool phenomenon with improper integrals. Just because one of your bounds is infinite doesn't mean your area is going to end up being infinite. The reason why is 1 over 9 squared looks really similar to that 1 over x function, except it looks something like this. And if I'm starting and I'm going from 2 to infinity, right, infinity's way over there, I'm finding this area. Now, once again, we might think that, because this never actually reaches 0, that means I'm adding an infinite amount of area, and so this value should be infinite. But the reason why this works is because I'm approaching 0 so fast that the area doesn't actually grow to an infinite amount. Instead, it just approaches a finite value. Okay? A good way to illustrate this is if I'm standing facing a wall and I want to walk towards the wall, but each time I only walk half the distance, am I ever going to reach that wall? No. Even though I could take an infinite number of steps, I will still never actually reach the wall, which means I've only gone a finite distance. So even though I'm doing an infinite number of steps, I'm still only going a finite distance. So that's how these integrals work. Even though my integral goes to an infinite value, the area under the curve still ends up being finite. One of these really cool phenomenon with improper integrals. Now, of course, that's not always the case. Let me give you a pretty obvious example where it's not going to be the case. Let's go from 1 to infinity of, x squared dx. The reason why this area going to be finite? Absolutely not. This area definitely ends up being infinite. Why? Because we know what the x squared graph looks like. The x squared graph looks like this. If I start at 1 and go to infinity, since my y values are getting infinitely large, of course the area is going to end up being infinite. So it's not every time, but some of the times your area still ends up being finite. And it's kind of up to you to figure that out by actually calculating the integral. So next I want to relate this back to something that we talked about in our last video in 5.2. Accumulated value of a continuous income stream. Okay, how much money are you going to have in an account if you're constantly investing money into an account in regular intervals, right? If every year you're putting money into an account. And so if you remember, we came up with these formulas both for present value and for future value, depending on what that continuous income stream is and how long it's in. Well, what if we weren't looking at specific years in advance? What if we said, I want to set up some sort of trust fund to where I'm always going to be putting in this amount each year for the foreseeable future, until the end of time, right? We use the word perpetually. So I'm going to set up a fund that perpetually adds a certain amount of money into an account each year. Okay? So we call this a perpetual income stream. Well, what would that mean? That would just mean that these t values end up being infinite. My upper bound ends up being positive infinity. Okay? Well, notice with future value, I end up having to plug in that infinity to this outside function right here, e to the kt, and guess what I'm going to get out of that? I'm going to get infinity. And so with future value is actually impossible to calculate with this, because if you're setting this up perpetually, then you don't actually have a set stopping point. So how are you supposed to calculate future value if there's no end in sight, right? So future value is impossible to calculate if I have a perpetual income stream. But take a look at what happens when we have present value. Okay? So let's look at present value. I want to let this be a perpetual income stream with some sort of income stream, right? That's what that's the R of t represents how much are you actually putting in each year. Now, like we said last time, this integral gets pretty complicated if r is non-constant. If I'm changing how much I'm actually putting in each year, this becomes hard. Okay, so to simplify things, and you'll see this in the homework as well, we're going to go ahead and just assume that we're always adding the same amount. So we're going to assume r of t is constant. Okay, that means I can rewrite this as the integral from 0 to infinity of just r e to the kt, right? R doesn't depend on t, so it's not a function anymore. It's just a constant value. And when we do that, if you remember, we have a nice simple formula for this. My formula is r over k times 1 minus e to the negative k times capital T. But in our case, what's capital T? I'm letting this go on forever. I'm letting it go on indefinitely. So I can go ahead and plug in infinity for t. Ooh, so does that automatically mean this is going to be infinite? Well, look closely. Let's see, I get r over k. So I'm going to, since I don't have an r value or a k value, I'm just going to leave those the way they are. But inside here, I can rewrite, since I have a negative in my exponent, I can rewrite this as 1 over e to the k times infinity. Well, what's k times infinity? Since k is just a constant, if I multiply that by an infinitely large value, of course that's still going to be infinite. So I can go and replace this with infinity. So what's happening to the denominator of this fraction? What's happening to the denominator? The denominator is getting huge because I have this e to an infinite power. My denominator is getting huge and my numerator is staying constant. So what's happening to this fraction? It's approaching 0. That fraction is just approaching 0. That means that all that I'm left with is r over k times 1 minus 0. Well, 1 minus 0 is just 1, and all I'm left with is r over k. So if you have some sort of continuous income stream that's constant and you're letting it go on perpetually, it's actually really simple to calculate the present value. All you have to do is just take your income, take your constant income stream, and divide it by whatever interest rate that you're investing in it. Okay. So just real quick, if I plan on investing $3,600 every year perpetually, right? If I'm setting up one of these trust funds to where I'm just going to let it go indefinitely, and my interest rate, I'm able to find a 4% interest rate. Once again, I can't find future value because there is no set future, but I can find present value. Okay? My present value is just B equals R in my case is that whatever that income stream is. So in our case, it's $3,600. That's how much I'm adding per year. K, of course, is the interest rate, so I'm going to divide it by 0.04, and I get $90,000. What does that mean? It kind of means that if I'm able to do this, it's worth me having $90,000 right now. It's kind of the same amount, same equivalent amount as if I just had $9,000 sitting around. Okay, that's it for 5.3. Our next video will be a lot different. We're just going to be going through some basic statistics using a worksheet. So look for that one. Have a great day, guys.